Thank you. So my name is Francesco, and so, well, apparently I'm opening up this spotlight session. So what I would like to show you here is some work I've been doing at the intersection between, well, computer science and engineering. Ta-da. And yeah, so, well, let's just start. First of all, who am I and what am I doing? So I'm a PhD, second-year PhD student with the University of Genoa, and that's, well, sunny Italy, and I'm with the robotics department. And then I'm also here. Well, it's less sunny, but and nevertheless, it's a nice place. And I'm with the computer science department there. So what is my research about? So what I'm doing is, broadly speaking, you can see there, formal methods in robotics. So actually, what does that mean? So it means that I'm a robotics engineer who at some point decided to go a little bit more formal than usual. And now, well, yeah, I'm trying to to come up with something reasonable in here. I hope I will not spoil it. So formal methods in robotics, it's actually, I mean, it's a very broad definition. So I will try to show you a little bit more in detail what I'm trying to do. And I will start with the robotics application that we are targeting. So here you see a picture of the RoboCup Logistics League, which is a fairly well-recognized and well-known benchmark in planning, so artificial intelligence planning in robotics. And what is the goal here? Well, you have a fleet of mobile robots which basically they receive orders at runtime, which means at runtime there will be an artificial intelligence, so to say, posting orders, and then robots will have to move around this simplified factory shop floor. And basically what they have to do is move from one machine, which you can see here, I mean just one of them, so they move from one machine to the other, and they have to complete all the processing steps so as to be able to deliver the requested product at the end. Now, of course, this problem can be solved in many different ways. There are already some approaches solving the problem, but the point is that those approaches are heuristically driven. So that means that basically we have no guarantees on the quality of the solution they come up with. So what we decided to do, which you see depicted here, very high-level description. Well, it's not a description, is it? Anyways, we decided to, first of all, take this fairly recent technique of, it's called optimization modular theories. So that's basically SMT, satisfiability modular theories, plus optimization. And that's one step, which you see somehow depicted here. And we decided to integrate this synthesis with optimization modular theories with an online execution and monitoring agent. So here is, let's say, this part. You see let's say, the engineering part. And here you see so we start from a model which describes the domain. I will not go into the details because if you want to see it, then you can come to the poster. But then, first step, we try to synthesize a controller. Now, if with optimization modular theories, as I said. Now, if synthesis succeeds, then, well, we have a controller now. But the problem is that, I mean, of course, it's not, the problem is not solved, right? Once you have a controller, then you still have to execute on the real concrete systems on the robot, right? And at that point, execution, it gets tricky. So what we decided to do, we integrated this first part with the second part, where basically, first step, okay, we have a controller, then we give it to an online executive. The executive is basically responsible for the execution of this controller. So the executive will dispatch, let me say, the required actions to robots, and robots will start executing. But then, now we have another problem, which is, what if the assumptions we had in the model originally do not hold in the concrete system? This, for example, might be due to, I don't know, some changes in the environment, say, a machine breaks or something. And that's why we have the other block, the monitoring block, which monitors the execution. And if everything goes fine, then we keep executing. Otherwise, we go back there to the model and we update with the new knowledge that we acquired using this block. Now there is one last block which I didn't mention, that is explanation. So assume the controller is not synthesizable for the given condition, then we would like to be able to explain to the human user why is it that the controller could not be synthesized for this scenario. So here, of course, once again, I will tell more during the poster session. We have also this additional ambition, that is to generate explanations so as to explain why the controller was not realizable. So yeah, that's it. So if you happen to be interested, then please come and see me and we can discuss what we are doing. So thank you. It's not that the controller is not enough. The controller per se specifies what the robots should do, but then the problem of executing the controller is basically a completely different one. So, and that's more of an engineering problem, like how to execute the controller that you synthesized. So that's what I wanted to.
But somehow the term controller seems strange to me, because then I can say who's going to execute the executive. I mean, you can keep going like that. Controller is usually, we think of it as the executive. Maybe a better term would be strategy rather than controller.
Or a plan.
Plan?
Yeah.
Okay.
So
controller already sounds like someone who executes.
Yeah. So it's true, actually. I mean, the point is that also there is no, I would say, uniform definition. So I completely agree. I mean, that you can see as a plan, and that is actually what you do in, if you speak with people in robotics. A controller is actually something that is low level, while the controller that was there, it is not low level, right? So, yeah, right.
Okay, thank you.
Thank you.
Hi, I'm Marijana Lazic. I'm from TU Vienna, and this is joint work with Igor and Josef. They are my advisor from Vienna, and Roderick from TU Graz. We were working on synthesis and verification of distributed algorithms, and namely we were considering parameterized case. This means that we consider a system with any number of processes. Usually we say n processes. Among them, f are faulty. But since usually we don't know how many exactly are faulty, we say there is an upper bound t, which is one additional parameter. So there is no more than t faulty processes. Usually we have some relation between these parameters. We call it resilience condition. And when I say that the distributed algorithm is correct, this means that for any value of n, t, and f of these parameters that satisfies the resilience condition, the whole system where correct processes will follow the algorithm and the faulty one can have arbitrary behavior, the whole system will satisfy specifications. And this is one typical example of an algorithm we consider. And I don't want you to read in detail this algorithm. I just want to show you the general structure. So processes are communicating by sending messages. And then they are counting how many messages they receive. And then only when this number of received messages reaches a certain threshold, then they are allowed to move. So for example, it says, if I receive t plus 1 messages, then I can do something. If I receive n minus t messages, then I can do something. So these expressions, we call them thresholds or threshold guards. And these are typical structures of the class of distributed algorithms we consider. We call them threshold-based distributed algorithms. And we have many examples of algorithms of a similar structure. And we have a tool, it's called Byzantine Model Checker, that successfully verifies both safety and liveness specifications of such algorithms. And now when we know how to verify them, we were wondering, can we also synthesize these algorithms using this verification technique? And I will also describe this verification technique at the poster. So we mentioned today this phenomenon, which is also in distributed algorithms very common, that people just use black magic and come up with an algorithm, and we actually don't understand why this is, where does this number come from? Why t plus 1? Why n minus t? And it must be very difficult to come up with these numbers because the algorithm should be correct for any n, t, and f. So we were wondering exactly how can we come up with these numbers? How can we come up with the thresholds that will make the algorithm correct for any n, t, and f? So we only know that these are some linear expressions over parameters, and we want to find a technique that will automatically synthesize them, so that we'll automatically find them. So this is the general goal. We want to synthesize a distributed algorithm, to synthesize this threshold that will give us an algorithm that is correct for any values of parameters for any n, t, and f satisfying certain resilience condition. So as an input, we give this sketch. So you can see this is as a sketch. So it's an algorithm with some holes. But we know that what is the structure of a hole with these question marks. And we give a specification and a resilience condition. What do we want to find? We want to find what are the exact values of this question mark. What are the concrete rational numbers? If we use them instead of question marks, we will obtain thresholds that will give us an algorithm that satisfies this specification for every n and t satisfying resilience condition. In order to do this, we developed this loop that contains two parts, a generator and a verifier. So a generator should guess a solution, guess one option, and then the verifier should check. And we do this, we loop this. So generator guesses, and then checks, and guess, and check, and we go like this. But the generator has an infinite search space because every question mark can be any rational number. So if we just use this naively, guess and check and guess and check, we do not have any guarantees that this loop will ever terminate. So we solve termination problem because by understanding that there is no reason to consider all possible options, all possible values of these question marks. We realize that some threshold that we obtain will not really make sense. Because what does it mean, for example, if you obtain a threshold -5? You should wait for -5 messages? What does it even mean? So we realize that we can consider only guards that we call sane, and those are guards that make sense, and they will give us bounded search space. But still, if you have bounded search space, if you want to enumerate all possible options, it will be too much. It will not be efficient. And how do we improve efficiency? Well, we make sure that the generator learns from every counterexample it receives. Every time it receives a counterexample, it will discard some part of the search space, and that's how we will improve efficiency. These are the main ideas, and you can check my poster today or on Wednesday, or ask me for the details any other day. Thank you.
Why your parameter have to be rational rather than integer?
And not integer? Well, you can also have integers, but usually.
Why they have to be rational?
The reason is that we in practice see that there are examples when you need, for example, n/2 or so. Yeah, for example, if you want to have majority, this is n/2, right? So this is 1/2 times n. So you do need rationals. If you restrict yourself to integers, it's even better. It's even easier.
So would it be more efficient if we just restrict your algorithm to integer?
Yes, but you will not see all solutions. Maybe this loop will tell you there are no solutions, but there may be rational solutions. You'll maybe miss some solutions by restricting it.
So one of the
most complex proof that I know for this kind of algorithm is for the Byzantine agreement.
Yes.
So, are you able to synthesize the algorithm for Byzantine agreement?
So here we used only, we have two benchmarks that we try to synthesize. So for verification, we have for many algorithms, but for synthesize what we tried, what I can tell you for sure that there are two algorithms, and the Byzantine agreement is not one of them. But actually,
have you been to verify mechanically Byzantine agreement?
well, if I'm sure what you're thinking about Byzantine agreement,
you
so
know that everybody has a value. I mean, the standard.
Like this one that I showed you at the beginning, this is also one version. It's something like this. So this is real. Okay, yeah. So
the key is to basically check. This is now very important because this is now blockchain does, right? This is
okay.
Byzantine agreement. And this is a kind of was always one of the benchmark of distributed algorithm, which typically one some of the most difficult proof. And I mean, epistemic approaches have been proposed. This is a big challenge. So I'm curious.
If it's you mean like a consensus?
Yeah.
So only yeah. So if it's impossible, yeah, we also cannot synthesize it, right? So, but all those of this form we can. But so there are some approaches like one-step consensus and similar things. Those we can also synthesize. But I mean, standard all possible algorithms which are of this form, we can certainly verify and synthesize. Well, the technique is meant to do that.
Okay, so more questions at the postal session. Thank you.
You're welcome.
How do you do that?
Well. Yeah. There. Oh, it went. Okay. Let's do restart.
2 minutes left.
Maybe just wait.
Yeah, everything is okay. So, any question? Yeah. So, infinite duration bidding games. I'm Guy.
Finite duration talk, but infinite duration game.
Yes. This is joint work with Tom Hensinger and Venci Chonev. So this is going to be about graph games. Graph games are very important in formal methods. I won't motivate them, I'll just tell you about them. So a graph game is played on a graph by two players, and the game proceeds as follows. So we place a token somewhere on the graph, and the players somehow move it throughout the graph, and this produces an infinite path. And this is, we call this infinite path the outcome, and this outcome determines the winner of the game. Okay, so this is a graph game. Now there are two classifications of graph games. One is according to the objectives of the players, so when does Lisa or Bart win? And the second is how the players move the token around the graph. So here are examples of how these are like rules for how the players move the token. And the simplest one is turn-based. So turn-based means that the vertices are partitioned between the two players. Whenever the token reaches a square vertex, then Bart is going to move, and whenever it's a circle vertex, then Lisa is going to move. Okay, what about objectives? So these are classic objectives: reachability, bookie, and so forth. In this work, what we do is introduce a new mode of moving, which is called bidding. So what does bidding mean? In bidding games, the players bid for the right to move the token. So how does this work? Each player has a budget, and for convenience, the budgets add up to 1. And in each turn, a bidding takes place, and the players simultaneously they submit bids, where a bid is legal if it does not exceed the available budget. And whoever bids higher wins the bidding. He gets to move the token, and he pays the other player. Okay, so this is I told you the bidding rules. Now, who wins the game? And this brings us back to this slide. So bidding is just the mode of moving, and we can study bidding with all the standard objectives. So this is a roadmap of the poster or the work. So reachability games were studied in the 90s. They're called Richmond games. This is named after David Richmond. There's also qualitative objectives. So here there is a winner to the game, and the standard objectives are bookie and parity games. And there's quantitative objectives. There is a value to the game, which can be thought of as the value that Lisa pays Bart. So one of the players wants to maximize this value, the second player wants to minimize it. Okay, so what questions do we ask on bidding games? So first of all, how much initial budget does a player need in order to win? That's like the first question you would ask. And the second question is, suppose a player has sufficient budget for winning, how does he win? Or how does he win? This means that we want to construct winning strategies or optimal strategies for the players. So I won't answer all these questions here. I'll give you a flavor of these games on something that was known. So this is from reachability games. So this is Richmond games. So this is an example. This is a reachability game between Bart and Lisa wants to reach the library, so this vertex, and Bart wants to reach that vertex, which is a skateboard. And we ask, how much initial budget does Lisa need in order to win? So let's give a first solution, which is an easy one. So if she has a bit over 3/4, then she wins. So how come? If she has a bit more than 3/4, then since the budgets add up to 1, Bart has a bit less than 1/4. Now we need to show a winning strategy for Lisa. In the first round, she's going to bid 1/4, which means that she wins because Bart can't bid over more than his budget. So she wins the first bidding. She moves the token one step right. She pays Bart. So Bart has a bit less than half, and she has a bit more than half, and we're in the second round. Now she bids everything. Bart again loses the bidding, and she wins the game. Yeah. Okay, can she do better than 3/4? Well, yes, she can do as low as 2/3. So if she has a bit over 2/3, then she wins. Why? Because then Bart has a bit less than 1/3. What she does is bid 1/3, which means that she wins the first bidding, as we saw earlier. She moves here, and now these are the new budgets. Right? She pays Bart. These are the new budgets. Now she bids everything. She has nothing to lose. If she wins the bidding, then she wins the game. And if she loses, so this is her bid. She bids everything. If she loses, we're back to here. And she gains at least this much, right? Bart overbids her bid, so she gains at least 1/3 plus an epsilon, which means that these are the new budgets. She has 2/3 plus 2 epsilon. And the key here is with the epsilons. So her epsilon increased by a factor of 2, which means that she can continue with this strategy and increase her budget until she reaches 3/4, and from there we know how to win. Great. Can she do better than 2/3? Well, no. And 2/3 is a special budget. It's called a threshold budget. If Lisa has more than 2/3, she wins, and if she has less than 2/3, she loses. And so we saw that in this vertex, there is a threshold budget, and we can ask, is this a coincidence? And it turns out that it's not. So the authors they show that threshold budgets exist. Every Richmond game, in every vertex, there is a threshold budget. Okay, so back to our questions. What we show is that both qualitative and quantitative games are reducible to reachability games. This uses a quite surprising probabilistic connection that was observed earlier. This turns out to be not that hard. The second question turns out to be much harder. What we show here is that the most technically challenging part is this, and is mean pair of games, and you're more than welcome to come to the poster session to see it. Yes?
Look at decision poker.
such game, given a budget, do you win? How difficult is that problem?
It's in NP and in co-NP. Because of a probabilistic connection, you can reduce it to so this is all going to be in the poster session, but essentially the probabilistic connection says that this game is equivalent to the following game. So the game is you choose which player plays next randomly. So you flip a coin, if it turns out tails, player 1 moves, and otherwise player 2. What's the probability of winning? That's exactly the threshold budget. And to simulate this game, you can do it using a simple stochastic game, and this problem is in NP and co-NP. Yep.
You don't know the budget of your opponent?
Very good question. So it wasn't studied. So this is a partial information game. In this context, it doesn't make sense because they add up to 1, but we have a follow-up work where it does make sense, and this is one of the things we want to do.
More questions? Thank you.
Okay, hi. So the problem, because I only have 6 minutes. Quantifier reasoning. SMT solvers are now regarded as the default solver when it comes to program verification. Why is that? Because it's very fast and it's push button, fully automatic. And deeply because it does contain with dedicated reasoning procedures, namely those theories. However, like most tools in the world, there's a limitation to it. Quantifier reasoning. Universally quantified formula basically unfolds to infinite structure of instances of this particular formula. So SMT solver can only store the instantiated formulas instead of the entire quantified formula for all. So that's our problem here. So like most tools in the world, they come up with improvised solutions. So these are known as triggers. The notation here is shown in green color. So it says basically, if you have this axiom, and if in your proof search space, you happen to find some term of this shape, please instantiate this axiom as well. This annotation added more control for the user. So now user can help the solver to find out the most relevant quantification instantiation. However, it's not part of the specification, so it doesn't really has any functionality per se, but it's a heuristic annotation needed for performance issues, and also often required user labor to manually write them. It's easier to show you in example. Say, if I have the axiom here for the SMT solver, and I have a ground turn A at number 42. So I'm going to mimic what happened inside the SMT solver. The first step is the pattern being matched. Hence, trigger an instantiation. Trigger further simplification inside SMT solver. And then generate a new ground term. Aha. This is actually known as matching loop. This problem has been discovered at the first paper of SMT solver by, I've got the paper, but well, this has been well studied, but there's no practical solution except for heuristic breaking of this loop. So now, hi, I'm Jeff. So I would present my work together with Carlo Fuglia. This is a work presented in IFM this year. So instead of using SMT solver, we try to verify the verification condition using first order theorem prover. For the pun, we have triggerless happy as our title. So instead of going through the traditional route of verification generation and then solving it using SMT solver, we opt for first order theorem prover. And we happen to have a very strong one in-house, Vampire. And by the way, it's currently just, I think, last week, open sourced. This is actually some cool thing. And because Vampire is a super precision resolution theorem prover, for this particular type of prover, quantifications are natively expressed inside the system. However, it wasn't used before as a program verification purpose because it doesn't really support arithmetic, for example. So you can only you can only axiomatize limited axioms like arithmetic. So we introduced BLT. Instead of being a sandwich, it actually stands for Boole-less triggers. In our paper and also in the poster, I can demonstrate that out of 19 problems we come up with trigger, the original toolchain managed to solve only 14 without trigger. And even if with the best trigger we can come up with, you still cannot solve the entire 19. And our system managed to solve all of them. So in short conclusion, we provide a fully automatic alternative to existing pipeline and reuse the front end of the pipeline without any adaptation needed. And it provides better quantifier reasoning without added annotation labor from the user. And if you really want to put your theory into work, you should really consider about hooking up with the intermediate layer. And therefore, you can extend your backend or your front end to various different of things. And try our system out. Thank you.
Is this really the first attempt to use Vampire for verification? I remember hearing about it years ago. I know people at Intel were trying to use Vampire for verification.
Yeah, they verify locally. So what we did is because we based our tool on the latest extension of Vampire, which handles assignment much more efficiently. Otherwise, the previous Vampire only support a very boring syntax where the assignment must be explicitly said, and then the state become explosion, then encoding itself become explosion in there.
More questions?
Thank
Thank you.
you.
Hi everyone, my name is Ayrat. This is joint work with Roderick Bloom and Sven Scheve, and I think it's the last presentation between Sandwich that you saw before and you. So, what is the problem we are trying to solve? It's a synthesis problem, and you already heard today from Bernd Finkbeiner about synthesis, and the synthesis problem intuitively is given a specification in some language, find a machine that satisfies it. So let's see what kind of specifications can be. So the first specification is, what is specification? Specification tells you what are the inputs of the machine. Here there is request, outputs, grants, and for example, LTL specification, here we have LTL formula. Always request is eventually granted. And if you give this to a synthesizer, it will produce something, not what you expected probably, but something like this. There is only one state where you just always grant and you don't read inputs. But it perfectly satisfies the specification. Now, to make it more interesting, you can consider more difficult LTL specifications, or you can go into CTL star specification, for example. So again, you have inputs, request, grant. And now specification says on all paths of the system, every request should be granted. And also we add this additional part which says on all paths, always there should exist a path where we eventually always not grant. So if you give this to a synthesizer, you will get something like this. 2 states, not grant, you read request, you go to grant. Here you don't read anything, and there is one self. So, okay. CTL star is more expressive in the sense that it allows you to write some structural properties. And but the problem is that if you look into LTL synthesizers, that there is in the synthesizer there are no CTL star synthesizers. Almost, there is only one. So LTL is a more widespread. So the question is, can we actually do somehow CTL star synthesis using LTL synthesis tools? And this is what we are doing. We reduce CTL star synthesis problem to LTL synthesis. How we do it? We are going to synthesize so-called explicit models. And these explicit models, in addition to satisfy the original specification, they also encode in itself the proof that the specification is satisfied. For example, we have some CTL star formula. What we do, we split the formula into subformulas, and for every universal and existential subformula, we introduce proposition. So it's just Boolean proposition, which a synthesizer has to find for us. And also, for each existential subformulas, we introduce a proposition which will encode the witness that this formula phi is satisfied in this particular state. So the LTL formula will say something like this. The top level proposition of the whole formula holds. So we want the whole formula to hold. For universal formulas, it's quite simple. Whenever we see that this state is labeled with this proposition, then from this state on all paths, the formula should hold. And finally, for existential formulas, it's roughly, but it gives you the idea. So if you see that in the current state the proposition holds, and you follow the directions that are encoded by this output, then this formula will eventually hold. Here's an example. So again, we have inputs request, outputs grant, and this formula, which you already saw before. And if you rewrite it, it becomes something like this. Inputs request, but outputs grant. And since we additionally add these propositions, we have more outputs. And the formula is at the top level. Proposition holds, and additionally, whenever the proposition holds, always PE should hold. And finally, whenever PE holds and you follow this direction, then eventually, globally on this path, you will see not grant. And if you give it to synthesizer, it will produce again system with 2 states, not grant, grant, and there is initially PA. This is PA. So PA holds, and because of this formula, PE also holds, and it will produce. It says go direction not R. If you go not R, actually. Then you will see eventually globally not grant. And that's the idea. And probably you wanted to ask this question. So CTL star and LTL are. CTL star is more powerful. You cannot reduce, for example, model checking CTL star to LTL model checking. So why we can do it in LTL? And the simple question is like there are 2 reasons, but the idea is that synthesizer has a control of the structure, and the synthesizer has we introduce new outputs. In model checking, we don't have these outputs. Okay, so some properties of the reduction. So it's if and only if reduction. The formula that we get in the end is exponential size of the LTL, but the synthesis complexity stays into exponential time, and the systems can get larger, and experiments. Interesting that if you do this reduction, the synthesis is even faster than the specialized CTL synthesizer, if the number of existential formulas is small. Thank you. Questions?
So LTL synthesis works by eventually reducing to a game and solving the game. So does it make sense to reduce CTL star to LTL or go directly to the game? Because essentially what you have described here is a reduction to the game, but
yes.
Now you have encoded the game in LTL, and my question is, why not go directly to the game?
Because if you want to go direct, so it's from the practical point of view. you want to go directly to the game, you have to put effort to make it efficiently. Implement this. It's just engineering work. And instead, we just want to use existing LTL synthesizers which do this engineering work efficiently. It's just a question of engineering. But we compared this with this direct approach which goes through the games, and well, it's okay, not through the games.
You give two complexity bounds. Are
Yes.
they exact upper bounds or well?
Yes, yes. So CTL star synthesis to expand time complete, so we don't lose anything in this transition.
More questions? Okay, so we do have another talk. You are not the last one.
I was the last but one.
People are very happy with this change.
No, it's okay. Parity Games is a turn-based game played between two players, usually called even and odd, on a directed graph. Player even controls the diamond's position, while player odd the square ones. And every position in the game is labeled with a priority that is a non-negative integer number. The goal of each player is to force a play along which the maximal priority visited infinitely often is of the same parity as the player, so even for player even and odd for player odd. And the position in the game can be partitioned into two winnings regions that are the maximal set of positions in which one player has a winning strategy and from which the adversary cannot escape. The solution of parity games is known to be a very important topic for a number of reasons. There are several applications in the context of specification, verification, and synthesis of systems. It is also a linear time introducible with the model checking calculus. It is a very challenging problem from the complexity viewpoint, since it is still unknown if it is possible to solve it in p-time. The approach is based on the notion of quasi-dominion and priority promotion. The quasi-dominions come from the well-known notion of dominions that is also used for other approaches like dominion decomposition or big steps. And the dominion is a set of positions where a player has a winning strategy and it is closed for the adversary, namely the adversary cannot escape. Solve a game using dominions means to find a dominion, properly remove it from the game, and iterate the search in the obtained subgame. So you are obtaining a small instance of the problem. Unfortunately, finding dominion can be as hard as solve the entire game. So the approach relies on a weaker notion of dominion called quasi-dominion, where the closure requirement is relaxed. Indeed, a quasi-dominion is a set of positions where one player has a winning strategy unless the adversary escapes from the set. The name of the approach, priority promotion, is given by the merging operation between a quasi-dominion and a dominion. The union of a quasi-dominion in a game with a dominion in the subgame, not in the entire game, is a quasi-dominion as well. this is an abstract game. The quasi-dominion are created in descending order of priority. So in this abstract game, the highest priority is 4. So a quasi-dominion of priority 4 is created, and it is open, and so are quasi-dominions 3 and 1. The first closed quasi-dominion in the sub-game is 0. The algorithm check where it can be promoted, and in this case to the quasi-dominion 4. And so it promoves the priority of each position in the quasi-dominion 0 to priority 4. This is the intuition of the operation of promoting priorities. We implemented the algorithm in the PGSolver tool, and it turns out that it's very effective, both for time and memory consumption. These are random games, and the details of this test you can find on the poster. Thanks.
Questions?
How does it compare to other parity game solvers? I mean, you just compared to PGSolver, but in the recent years, lots of more efficient parity game solvers appeared.
Well, you asking for the implementation or the solver?
Because like PGSolver is like basically the baseline, and most of the tools are way better than PGSolver.
This is the problem. The point is that most of solvers are implemented into PGSolvers. So if you choose to use a different implementation, you must find an efficient implementation of all the solvers in that language. And currently, this is not possible. If you take, PGSolver is implemented in OCaml. If you use C++, for example, you can't find all the solvers. So of course, you can implement all the solvers, but no one have already done this. So I think that PGSolver is the right tool to have a comparison between the solvers.
So other algorithms work by reducing the number of priorities. And so I'm a little puzzled. What's the difference between reducing the number of priorities and priority promotion?
Well, if you know the recursive algorithm, the creation of the quasi-dominions is similar to the analysis of the recursive algorithm. But in the case of the recursive, it is strongly dependent on the number of priorities, because he find a solution of the entire game. So he go to the empty game and then go top to the highest priority. But in this case, in this case, you are not forced to analyze all the priorities. The first one that makes you close the quasi-dominion allow you to or close it because it is a dominion in the entire game, or perform a priority. So if you have others priority, you have not to analyze them. So a compression is less effective, but yes, could be